We have one more topic to wrap up to finish with everything we really need to know about derivatives. That last topic is the hyperbolic trig functions and their identities, the derivatives of them, and the hyperbolic trig functions. The development of the calculus of the hyperbolic trig functions very closely parallels that of the development of the calculus of trig. Hyperbolic trig and trig are very tightly related, and when we get through here we will have another set of functions which are almost like the trig functions, only they're the sinh, the cosh, the tanh, the cotanh, the sech, and the cosech, and we will have derivatives of those. We will have some identities that we will need to prove the derivatives, like we needed some identities to derive the derivatives of the inverse trig functions and such. And with those identities then we'll be able to polish off all the rest of the derivatives that we will need for this course pretty much. We will have finished up all of the elementary function derivatives and their inverses and their derivatives. Let's compare the trig functions you know with the hyperbolic trig functions. Back when we were working on just plain old trig functions, first there were definitions. Always in mathematics everything starts with a definition. Otherwise you don't know what you're talking about. So the sine was defined as opposite over hypotenuse, cosine is adjacent over hypotenuse, and then the other four trig functions were defined in terms of the sine and the cosine. And those are the basics of trig, and without knowing what those words mean, you cannot, and how they're defined, you can't work any trig problems. There's a very similar thing over here with the hyperbolic trig, although instead of defining in terms of pieces of a triangle, the sine and the cosine, and then everything else having a corresponding ratio on a triangle, the hyperbolic trig functions are defined in a very not quite normal looking way, I guess, which is they were defined in terms of exponentials. And you might ask why this whole hyperbolic trig thing was invented, and the answer is pretty much because they show up in science and engineering, all sorts of STEM fields. In particular, the cosh is the shape of a catenary, which is if you hang a cable or a rope or anything flexible that hangs, it hangs in the shape of a cosh, which makes it very important function. So over here we start out with the basic definition of the sinh and the cosh, and then tanh is defined very similar to the tangent. Instead of sine over cosine, it's sinh over cosh. The cotanh is 1 over the tanh, similar to the way the cotangent is 1 over the tangent, and you can look at the similarities all the way down. They're pretty much 1 for 1. And these are simply, in the green box here, these are the definitions of the hyperbolic functions. You should know what they are. They're not hard to remember. They parallel exactly pretty much the definitions for the trig functions. And then with trig we had some identities that were needed, and there were 3 Pythagorean identities which show up a bunch, and those were based upon really going back to the fact that these were based on a triangle and had an opposite side, a hypotenuse, and an adjacent side, and you can show based upon the definition of the sine and the cosine that this identity is necessarily true. And then from this identity you don't have to go back to the triangle. You can simply divide through by the cosine all 3 terms and come up with the second Pythagorean identity, and in a similar manner you can get the third one. There's a similar thing going on over here with the hyperbolic trig functions. Over here it's cosine squared plus sine squared is 1. Over here, it's cosh squared minus sinh squared equals 1. Don't like that. It's just a function of the definitions. It's just a fact of nature, so to speak, with these hyperbolic trig functions. They look very similar, except there's numerous sign differences. And what you would need to do is prove these things. Somebody said it's minus. Maybe they just made a mistake. Well, what you would do is you go back to the basic definitions up here with the exponentials, and you square the cosh exponential, and from that you subtract the square of the sinh exponential, and if you're working fairly decently with exponentials, you'll find out that this is actually true. And then you don't have to go back to the exponentials anymore. You can simply divide through by cosh squared of x to get the second one, and in a similar vein you can get the third one. Okay, so that's kind of the basic trig. There's a whole slew of, for every trig identity there's a corresponding hyperbolic trig identity, and we won't be needing those very much. So the next thing that comes up here is the derivatives of these things. So we know the derivative of the sine is the cosine. That's not a definition, that's a fact that is derived from what it means to take the derivative. These two in yellow here, they were hard won because they required using a limit of a difference quotient, which makes them very difficult compared to the others. After you have these two, we went through an exercise of deriving the remaining 4 using identities, trig identities, and what we know about differentiating in general, like the quotient rule and the product rule. A similar thing happens over here, where we actually don't have to work very hard to come up with the derivative of the cosh, because we can go right back up here and just differentiate it. If you differentiate this and you differentiate your exponentials right, you'll find out you immediately get the sinh, and vice versa, and there is no minus sign in that. If you want to come up with the sinh squared, then you can use the various identities just like you did over here, and you don't have to go back to square one to do that. And then we're interested in coming up with the derivatives of the hyperbolic inverse functions, and here are the derivatives of the inverse, the arc sine, the arc cosine. And notice a lot of these are repetitive pretty much. We really don't need two that look almost the same, because our big use for these is actually going the other way. It's when we do integration, when we see something that looks like one of these forms, we will know that the antiderivative is in fact the arc sine or the arctangent. Yeah. So you have the integral 1 over 1 minus x squared. It's the arctangent. If you don't know what an integral is, you'll find out next quarter. So that's pretty much the process that we're interested in, is just coming through and proving the derivatives of the inverse functions, and they're done exactly like they were done for the trig functions, just like all the inverse functions were proven.